the first thing we do when we are graphing is we find the derivative. So in an e to the x function, remember the rule is to just take the derivative of the exponent and then multiply by the original. So you'll have 2 e to the 2x. And then you're supposed to take that and set it equal to 0 and solve to find critical points. So in theory, I guess you would like divide by 2 and then you would try to solve this. If you remember how to solve e questions, you take the natural log of both sides to get rid of the e. So that would be, so when you natural log this and natural log this, you get 2x equals the natural log of 0. But, no, yeah, so I was going to get there. So this doesn't exist because remember yesterday we were looking at all the natural log properties. So that means that this is not solvable. So remember, if it's not solvable, that means we look at values for which the derivative maybe doesn't exist. So go back to your derivative. Is there anywhere this wouldn't exist? So basically, what's the domain of e to the x? It's an exponential growth function.
So negative. No.
Can we plug in a negative?
Yeah.
Can we plug in a positive?
Yeah.
So that means it exists for all real numbers. So all that means is that there's no critical points, which is weird. So we haven't done that yet. But that doesn't mean we can't test concavity. So if you look at your first derivative, you're just going to pick whatever, like anything. 2. Plug it in. If you plug in 2, do you get a positive number or a negative number? Positive. So it's positive everywhere. So it's increasing everywhere. And it's never decreasing, which makes sense because, like I said, it's an exponential growth function. Yeah.
What if we accidentally write like positive infinity to negative infinity? That's still everywhere, right?
It is, but it's not right. It'd be like a notation, points off for notation.
Yeah.
So basically, if it's e to some constant times x, if the constant's positive, it's going to be increasing everywhere, and if the constant's negative, it's going to be decreasing. And if it's something else, then it's something you could have solutions. So I'll go over like a situation maybe where you'd have a solution. So, but we need to do the second derivative. So second derivative. So we're looking at this. So we want derivative of the exponent times the original.
So 4.
Yeah.
e2x.
Now, can we set that equal to 0 and solve that?
Yeah.
Yeah? So 4e2x.
We're not going to get anything.
Right. Okay, so we're not going to get anything. So no solution there. So we'll do another derivative test. Same thing. Pick any number.
2.
2. When you plug 2 in, do you get positive or negative?
Positive.
Positive. So that means it's concave up everywhere. So it's increasing and concave up, and then in theory, you should know that both of these functions have asymptotes.
Yeah.
In theory. Now, this one has a restricted range because there's nothing that we can plug in for x that's going to give us a negative number or even 0. So we have an asymptote at y equals 0. Pretty much for all e to the something, e to the constant times x, you're going to get an asymptote of y equals 0 unless there's a vertical translation. So if it says like plus 1, your asymptote will move up to 1. If it says minus 1, your asymptote will move down to negative 1. So ours is at 0. So that's like something we can graph.
Wait, for concave up, I always confuse this. I feel like I've asked this like 25 times this year.
So it should look like a cup.
Yeah, this way.
Cup
like
up.
This, so
Yeah.
you're going up and then going down.
Right. We could find some intercepts maybe to graph. We know we won't have an x-intercept, so don't bother. Just find your y-intercept. So your y-intercept, you would just plug 0 in for x. So that's e to the 0. What's that? 1. So you have a y-intercept of 0, 1. Okay. Now, if you want, you can pick like another point to graph, or you could just graph it probably if you know a thing or two about what it looks like.
Yeah.
If it's increasing and it has to get closer to this asymptote, so it's going to increase this way, but it has to get close to the asymptote this way. and it has to be concave up, so it's going to look something like this. There you go. Okay. So, side note. Let's say your function is e to the x squared. Whoops, equals. So your derivative would be 2x e to the x squared, right? Or, sorry, derivative. You would set that equal to 0 to look for critical points. And this is a product of two things. So what you could do is use the zero product property to set each equal to 0. This one you won't be able to solve, but this one you get x equals 0. So you would have a critical point. So if the exponent of the original function, it has a degree higher than 1, you could have some points in there. So that would be a type of question where you would actually like have to do a test. So you do your test, and you'd get, if it's negative, it's negative, and if it's positive, it's positive. So it would actually like fluctuate a little bit. Okay, done with side note. All right, b. So b is a natural log function. So natural logs are inverses of e exponential functions, which means if an exponential e function has a horizontal asymptote, the natural log function will have a vertical asymptote. We discussed briefly over here that you can't take the natural log of 0. So whatever x value is going to make that 0, that's an asymptote.
Okay, so it's 2.
So 2. So you'll have a vertical asymptote going through x equals 2. So you can identify that whenever. If it just says ln x, then it would be 0. Otherwise, you're just basically taking what's inside and setting it equal to, well, setting it greater than 0, kind of, technically. All right, so then let's do the first derivative. So for this first chunk, we're going to do d stuff over stuff times 2. So constant times d stuff over stuff. So we got 2. What is d stuff?
X.
No,
Just 1.
just 1. And then over stuff.
Wait, why did you write 2?
Because there's the constant too.
Oh, okay.
Yeah.
And 2 times 1.
And then the derivative of 5 is nothing. So that's our derivative.
Okay.
So what we would do is take that, set it equal to 0, and try to solve. Can we solve? No. Remember that what we can also do is you would also possibly have a critical point wherever the derivative does not exist. So this derivative does not exist at 2. So that would be the only point you would put here. It's funny that it's 2 because you were picking 2 on the last one. So 2 is a critical point. Could be point of inflection, maximum, minimum, I don't know, we'll see. So if we plug in 3 into our first derivative, we'd get positive. And if we plug in anything less than 2, we'll get negative. Now technically, this function only exists for x values greater than 2. So even though when we do the test, we can get negative, nothing's happening over there. So there's nothing happening on this side of the graph. It doesn't exist over there. Which means we don't want to try to pretend like it's decreasing. It's only going to increase from 2 to positive infinity. So even though we can do the test, that doesn't mean that it exists over there. You have to kind of think about that. Let's look at second derivative. So in order to find the second derivative, I'd probably rewrite the first derivative as 2 times x minus 2 to the negative 1 power and use chain rule. So that would be negative 2 times x minus 2 to the negative 2 times the derivative of the inside, which is 1. So that's negative 2 over x minus 2 squared. Can we set that equal to 0 and solve? No. But this will not exist at 2. So 2 would be the point we would use. Now, the numerator is always negative, the denominator is always positive, which means this is always negative. But remember, our function doesn't exist over here, so we don't really care about that. So it is decreasing from 2 to
Wait, isn't that concave
infinity.
down?
Oh wait, yeah, it is concave down. Down. Yeah, 2 to infinity. All right, so if it's increasing in concave up or concave down, it's going to look something like that. So backwards of the last one, this one's not going to intercept the y-axis because nothing's happening over here. It's already like beyond the y-axis, but it will have an x-intercept, so we can find that, but I don't know that. I'm going to put the work over here. So we can find that by setting g of x equal to 0. Not going to be a nice number, but it's still something we can find. So you can subtract 5 first, and then we would divide by 2, so you get negative 2.5. And then you'd like e both sides, so you'd make both sides of the equation an exponent of e, so we have e to the negative 2.5, which is some icky irrational number, and then you add 2. So whatever this icky irrational number is, that's your x-intercept.
Yes, it's like 2.7 times that.
Something.
I need to charge my Calc.
I think it's like
2.08.
okay. So 2.08-ish is like right here. It's like really close to your asymptote. So then it's going to go up, hit your thingy, and then keep going up and out. It's going to get really close to the asymptote and keep increasing. Basically looks like the inverse of something like this. Okay, good? All right, so those are those. Then we got some word problems. The value in dollars of a stock T months after it is purchased is modeled by this. First thing it wants us to do is just to find some stuff. So we're just going to plug in 1 and plug in 12. It would be good to know what these represent. So what do these represent? V of 1 and V of 12.
How many stocks do you have?
Close.
What?
So V of T,
how much your stock is worth?
how much your stock is worth,
And how many you have?
1 month,
Oh wait, those are months?
1 month after, yeah, 1 month after it's purchased, and this would be the value 12 months after it's purchased.
Okay.
Okay, so plug that in your calculator. What do you get? It's going to be approximate.
58.
Okay. All right, then, so again, this would be the value of your stock after 1 month, the value of your stock after 12 months. Now we're going to find the derivative. So if you look at this as a whole, the derivative of 20 is 0, so don't worry about the 20. Just focus on the first part. And it's going to be, so just take the constant and we're going to multiply it by the derivative of the inside, so we can do that. So
negative.
this is going to be nothing, and then this,
It's going to be positive 1.1 times e to the negative 1.1.
yes. So this would simplify to, I don't know what 5.8 times 1.1 is. I should, but I don't. So 6.9?
It's 63.8.
What? I'm dumb. Okay, so there you go. So that would be your rate of change of your value of your stock after a period of months. This particular function is always decreasing, so that means that your the value, while the value is the value like has increased, it is like the rate of change of it increasing is decreasing. Okay. After how many months will the value of the stock first reach? Oh wait, so actually, hold on, let's go back a second. So this is decreasing, but it's always positive. So this function is always positive, so your value is always increasing. I'm thinking the second derivative. So the second derivative would be always negative, which means while the rate of change is increasing, it's increasing less quickly as time goes on. All right, after how many months will the value of the stock reach $75? So this is a value, this is a V, so you're gonna plug that in for V of t into your original equation and solve. So we're just kind of working on solving. It's like algebra 2 stuff. So first step would be to subtract 20. So 75 minus 20 is 55. Then divide and you get whatever, 55 over 58. I'm just going to leave it like a fraction. And leave enough space. Then you can subtract 1 and you'll get negative 3/58. And then you want to divide by -1, which is really important, otherwise you're not going to get a solution. So divide by -1, that makes both of those positive. Take the natural log of both sides. So you get the natural log of 3/58 equals -1.1t. And then just divide by -1.1.
Um, 2.69.
So about, I guess we could round up. We'll say about 3 months. Because at 2 months it won't quite be there. So after 3 months, value of the stock will reach $75. Okay. Next thing it wants us to do is find the limit of the function. So you're finding the limit as t approaches infinity. Whoops. Of 58 times 1 minus e to the -1.1t plus 20. Essentially what you're kind of doing is finding the asymptote. When you find the limit as like x approaches either infinity or negative infinity, you're finding some kind of asymptote. It goes both ways. That's the definition of asymptotes, is like the limit as either x or y approaches infinity. In order to do this, we would need to rewrite this part in order to kind of like evaluate it. So to rewrite it, you would write it as 1 over e to the 1.1t because it's a negative exponent. That's what actually gives it a limit. So if you remember, in theory, if you were to plug in like a billion here, that would make this a really tiny fraction, right? So this whole piece right here, as t approaches infinity, it becomes 0. It approaches 0. So we have 58 times 1 minus 0 plus 20 is our limit. So that's just 58 plus 20, which is 78. Which if you look at, remember we plugged in 12 and we got like 77.9 repeating. If you plugged in like 13 and 11, you'd see like it was approaching 78. So basically what that means is that your stock over a long period of time isn't going to be worth more than $78. There's almost like a limiting value for your stock value in this example. Ta-da! Okay. Questions? Okay. So you see how all that limit stuff worked. If this was not negative, we wouldn't be able to find the limit because it would just approach infinity. So, because being able to do this, that makes this like go away and allow us to actually find the limit. That's important. Is a marginal profit example. Do you remember how to find marginal profit?
Yes.
How?
So I have to do like the derivative.
The derivative. So basically it's just finding the derivative. So this is our function. The derivative of 2x is,
2.
yeah, and then the derivative of this second piece, that requires the product rule.
Yeah.
There's two ways you can do this. You can add what we're about to calculate, or you can subtract what we're about to calculate. I think it's easier to add and then look at first as a negative number.
Yeah.
And we won't screw it up. So first is negative 0.3x and second is ln x. So we're going to do first d second. So what's d second?
1 over x.
Yes. Plus second. And then d first is?
Negative 0.3.
Yes. Okay, and then we just need to simplify this a little bit. If you combine these two together, the x's cancel, so you'd have just negative 0.3, and that 2 and the negative 0.3 make 1.7. Then over here, this is actually negative, we'd get minus 0.3 times the natural log of x. That would be our marginal profit. So calculator, plug in 150. Okay.
Or
And
0.28.
And so in this question, it says that this is the profit in thousands of dollars. So if you get 0.19, that's technically 0.19 thousand. So in dollars, if you just kind of move the decimal place 1, 2, 3, that means $190. Which is it's kind of awkward. So yes, not that much money.
You think you get more from mechanical pencils and so many.
Well, this would be one. So this would be how much more money you would get for selling 150 instead of 149.
Right.
1,000. 149 because it's in thousands. So
like
from
$40 difference.
but it's a big difference. So between 149,000 and 150,000, you're making an additional $190. I guess it's not that much money. How many thousands of mechanical pencils should be sold to maximize profit? So how do we maximize profit? How do you find the maximum? How do you find the maximum of a function?
Equals 0.
Yeah, what's it?
Derivative.
Yes. Dropped your pencil.
I was so like,
All right, so our derivative was 1.7 minus 0.3 ln x. Set that equal to 0. You can add the 0.3 natural log of x. Divide by 0.3. And then e to the 1.7 over 0.3 is going to be our x. So what is that?
5.66.
So
But I didn't do the e to the x though.
oh,
That's
okay.
just,
So e to that.
yeah. What?
So bigger than that.
289.
So that means 289,000 pencils because it's in thousands.
A lot of pencils.
Oh, that is a lot of
If
pencils.
you plug that back in,
It'll give you your
to the
maximum profit.
oof. Hold up.
289, not 289,000. It's like Ticonderoga. They got a good system going here. $86.7 thousand. There you go. That's not enough money.